Hello mathematicians. We're going to now have a look at an introduction to linear equations and inequations. Now we already know about solving equations, and linear equations, of course, we solve in exactly the same way. That if we take something across the equal sign, we reverse the operation, and we take things across the equal sign in the reverse of the usual order of operations. The other way that we can often think about solving equations is that what we do to one side of the equation, we also need to do to the other side in order to keep it balanced. So both are equivalent points of view, it's just a matter of which one suits your thinking in a particular case. If the equation involves fractions, you might also recall from junior school or the section on algebraic fractions that multiplying through every term by the lowest common denominator will eliminate all fractions and just make the process easier. Linear inequations use exactly the same processes, but we've got a few extra conditions that we need to be concerned about. The first is that if both sides are multiplied or divided by a negative, or alternatively, if you take a negative across the inequality under the process of multiplication or division, the direction of the inequality changes. Now the reason for this we'll come back to. It's a fairly straightforward rule. And the second one is if the reciprocal of both sides is taken, the direction of the inequality changes. Now, if you get into an exam and you're stuck about trying to remember what exactly the rule is, go with an easy example. So if, for example, we think of the inequality 4 is greater than 2, just working straight out with numbers, then if I divided both sides by a negative, say negative 1, so that I got negative 4 and negative 2, then no longer is the inequality pointing to the right true. I know that negative 4 is less than negative 2. It's further to the left on the number line. So dividing both sides by a negative actually requires that the direction of the inequality changes. Likewise, again as a simple example about the reciprocal, if we had something like, we know for example that a third is less than a half. Now if I take the reciprocal of both sides, I flip this one upside down and I flip this one upside down, clearly now 3 is greater than 2. So as I said, these are not proofs by any means, but they're just little reminders, examples that we know are true, and we check that we do actually know what to do with the inequalities. So let's have a look at putting some of these into practice. So we'll just do some of these, hope that they're reasonable ones. So if we do C, now if this was an equality, we know what the process would be. We'd bring our 3a across to the other side, so we'd have 16 plus 12a is greater than 10. And although I was bringing something across, and I was saying it was subtracted here and it was going to therefore be added over there, I'm not multiplying or dividing by a negative, so there's no reason to change the inequality. When I take the 16 across to the other side, again, well, that gives me that, and I then divide by 12 and I get that, there's still no reason for the inequality to change, because I wasn't taking reciprocals and I wasn't multiplying or dividing by a negative. So no worries with that one. Let's try E and see what happens. I'll just take this up here. So 13 minus 12x greater than or equal to 6 minus 3x. Let's take this negative 12x across and add it. So I've got 13 greater than or equal to 6 plus 9x. So take the 6 across and subtract it. 7 greater than or equal to 9x. take the 9 over, so I've got 7/9 greater than or equal to x. Now, one thing which wasn't covered in those rules up above is the logic of a statement like this. So while it's true, 7/9 greater than or equal to x, for inequalities, we usually make sure that the x is on the left-hand side. And if I do that, that means because 7/9 is greater than or equal to x, x is less than or equal to 7/9. So just think about what common sense and your logic tells you to do about these. We'll do the last one, see what happens there. So in this, if I expand the brackets out, we've got 8 plus 8 minus 4x greater than 3 minus 10 plus 2x. I'll gather the x's to the same side, and just, not because it's the way I would usually do it, but let's take the 2 x's over to here. So I've got negative 6x there, and I'll take this 16 over and subtract it. So over here I've got 3 minus 10 minus another 16, so that's minus 23. And now, to actually get the x by itself, I've got to divide this negative 6 across both sides. So because I'm dividing by a negative, I change the inequality. So x will be less than negative 23 divided by negative 6, which is 23 over 6. Now there's a fair bit packed into this exercise. So as well as inequalities or inequations, they're talking about changing the subject of a linear equation. And that's also sometimes called transposing. Changing the subject follows exactly the same techniques and rules as solving an equation, except all that we do is the rearrangement. We're not after the value of the pronumeral because we haven't got enough information. We're just changing the way the pronumerals are combined so that the subject, the thing to the left of the equal sign, is whatever we're told it has to be. So let's have a quick look at these examples. Okay, so for our first example, I'll just do it down here, we need b to be the subject of the equation, which means we need the b by itself. So to get the b by itself, I first of all need to shift the d by adding it to both sides. So a plus d equals bc, and then get rid of the c by dividing. So therefore b equals, and again, I don't have to shift the b to the left, but I will, it looks nicer. So dividing both sides by c, I get that b equals a plus d on c. Notice with the equality as opposed to the inequality up here, there's nothing to do when I shift from one side to the other. Now example B, we wanted n to be the subject, and n is stuck inside those brackets. So if I successively get rid of material, I'll get rid of the a first, so t minus a equals n minus 1 in brackets times d. Then I'll get rid of the d, t minus a on d equals n minus 1, and then I'll get rid of the 1. So t minus a on d plus 1 equals n. Now be aware that there are different ways in which the left-hand side could be written, and the textbook may do this in the solutions. So for example, they might decide to put everything on the left-hand side over the common denominator d. And in that case, we would have t minus a plus d all over d is what n is equivalent to. Both of these are acceptable. We just need to be able to see when two different forms are equivalent. For our example up here, if we want r to be the subject, then at the moment r is part of the denominator here. We need it to get it up the top of the equation. So we've got two possibilities. Take the reciprocal of both sides, or multiply q plus r, because there's really a set of brackets there, across to the other side. It makes no difference in this case which process you choose. Just for variety, I'm going to do the flip. So q plus r on p equals 1 on t. Therefore, q plus r equals p over t. I've multiplied this p up. And therefore r equals p over t minus q. Or if they decided to put it all over the one denominator, that would be p minus qt all over t. And our last example here, we want v to be the subject. So in this case, I would shift the 1 first of all. So u minus 1 equals 3 on v. Again, I could take the reciprocal of both sides, but for variation, this time I'll imagine multiplying the v up. That will get it to the top, which is what I need. So that would be v times u minus 1 equals 3. Therefore, v equals 3 divided by our u minus 1. Now you'll notice that I'm not writing the brackets here. It's no problem if I do, but because this line is right along, the implication is that u minus 1 is one term down there. Okay, so have a go at 1f.